Today we are going to discuss about the toroid. Toroid is a endless solenoid. We know that a current carrying solenoid acts as a bar magnet. One end of the solenoid acts as a north pole and other end acts as a south pole. So if we bend the solenoid in the form of circular ring, then what happens? Both the free end of the solenoid come close to each other and they attract because of opposite polarity and will take a form like this. মই আৰু এবাৰ ৰিপিট কৰিছোঁ, যেতিয়া এটা সলেনয়েডৰ মাজেৰে কাৰেণ্ট যায়, সলেনয়েডটো এটা বাৰ মেগনেটৰ দৰে বিহেভ কৰে. One end of the solenoid acts as a north pole and other end acts as a south pole. Okay? Now when we bend the solenoid in the form of a circular ring, both the free end of the solenoid come close to each other and there is a net force of attraction between them and take a shape like this. And this particular current carrying coil is called a toroid. So what is the significance here? So in order to know the significance of toroid, initially we must know the limitation of the solenoid. In solenoid, magnetic field induction in this part is very strong. Along the axis in the central part of the solenoid is very strong. But magnetic field induction here and here very weak. Why they are weak here? You just see the magnetic field lines separated from each other. The magnetic field lines emerge from this end and they get separated. At this end, magnetic lines of force enters, but here they are separated from each other. That means magnetic field induction in these two regions is small compared to the magnetic field induction along the axis and central part of the solenoid. Our magnetic field here and here very weak. Therefore, with the help of a solenoid, we cannot produce a very strong magnetic field. So therefore, we bend the solenoid in the form of circular ring, so that we get this particular structure. So here, we get this particular structure. Here, magnetic field is very strong here, and magnetic field here and here, 0, because not a single lines of force comes out of the toroid. Because lines of force will flow like this, move like this. Initially, say this is the north pole, this is the south pole, the lines of force, the north pole, this is the south pole, the lines of force will go like this. So since not a single lines of force is outside the coil of the toroid, a very strong magnetic field is produced in this particular region. Therefore, to obtain a strong magnetic field, we have to use the toroid. And toroid is nothing but a endless solenoid. Endless. Toroid is a hollow circular coil of circular ring or circular coil of many turns. And it is an endless solenoid. Let the total number of turns of this particular toroid is capital N. Total number of turns in this particular toroid is capital N. We have to show that magnetic field is very strong and uniform here. Magnetic field is 0 outside the toroid and magnetic field is 0 here also. By using the Ampere circuital law, we have to prove that magnetic field exists here and very strong. Magnetic field outside the toroid and magnetic field in the central part of the toroid. In the central part of the toroid is 0. And during this derivation, we assume that the thickness of the toroid is very, very small. Thickness of the toroid is very, very small. If the thickness is very small, radius of this inner part and radius of the outer part can be taken equal. If the thickness of the toroid is very small, then radius of the inner part and radius of the outer part, radius of the inner part and radius of the outer part can be taken equal. So in order to apply the Ampere circuital law, in this case, I consider 3 Amperian loop, one in the central part of the toroid, one outside the toroid, and one is along the axis of the toroid. So this is the cross-sectional view. This is the cross-sectional view of the toroid. Okay, these are the wires. That means if we cut the toroid along this plane, and along this plane, and upper part is taken out, then what happens? We are only obtain the lower part, and this is the lower part of the toroid. So this is one, okay, this is one wire, and this is one wire. The cross means current enters through this wire, and dot means is coming out. Here also, so this is this part of the wire, this bend line is this part of the toroid, this is cross, that means current enters through this wire and it taken out. Okay, so we assume that this thickness is very, very small. Therefore, I consider 3 Amperian loop at the point P, at the point Q, and the point S. I consider 3 Amperian loop at the point P, at the point S, and at the point Q. The point S is along the axis of the toroid, and point P is in the central part of the toroid, and point Q is outside the toroid. Since this thickness is very, very small, thickness of the toroid is very small, we may consider that the radius of this Amperian loop, and radius of this Amperian loop equals. Since the thickness of the toroid is very, very small, radius of this Amperian loop, and radius of this Amperian loop are exactly equal. Let capital I be the current passing through each turn of the toroid. Capital N is the total number of turns of the toroid. Now, at the point S, so this is the direction of lines of force also. Because the magnetic field is inside the toroid, and since the toroid is circular in cross section, so therefore lines of force is also circular. So this is the direction of B, and this is the direction of DL. So here at the point S, direction of B and direction of DL, they are parallel to each other. So B dot DL is B DL cos of 0. Okay. At every point on the axis of the toroid, at every point on this Amperian loop, value of B is constant. So therefore B is taken out of the integration. So what is integration of DL? Integration of DL means this is circumference of the Amperian loop. In this particular case, our Amperian loop is circular. So what is integration of DL? Integration of DL is nothing but circumference of the Amperian loop. Circumference of the Amperian loop is twice pi r. That means if we take B dot DL at the point S at the point S. If we take B dot dl at the point S, what we get? B into twice pi r. B into twice pi r. Okay? So, now, what this Amperian loop encloses what current? These wires 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? This Amperian loop encloses what current? This Amperian loop encloses these wires. Therefore, the current passing through these wires is the current inside the Amperian loop. What is the total number of turns here? Don't count in my figure. Total number of turns is capital N. That means how many wires are like this? The N wires are like this. So what is the current inside the Amperian loop? Current inside the Amperian loop is Ni. Current inside the Amperian loop is Ni. Current inside the Amperian loop is Ni. So what is the Ampere's law? Ampere's law is the line integration of closed line integration of closed, this is the closed, the closed line integration of B dot dl, but line integration of B dot dl around any closed path. Line integration of B dot dl around any closed path is equal to mu 0 times current threading the surface enclosed by the closed path. What is Ampere's law? Line integration of B dot dl around the closed path. Around the closed path means around the Amperian loop is equal to mu 0 times current threading the surface enclosed by the closed path. So what is B dot dl in this case? What is B dot dl in this case? B dot dl is B into twice pi r. What is the current inside the Amperian loop? This is the Amperian loop here. For the point S, this is the Amperian loop. So how many wires are there? These wires are there. How many wires? Since the number of turn is N, so N wires are there. Through each wire I current flows. Through each wire I current flows. So therefore what is total current? Ni. So therefore B into twice pi r is mu 0 Ni. So what is B? Mu 0 Ni by twice pi r. But if I call N is the number of turns per unit length of the toroid, then what is the total? What is the total turns? What is the circumference of the toroid? Circumference of the toroid is twice pi r. What is N? N is the number of turns per unit length. So total number of turns of the toroid is key. Total number of turns of toroid is equal to circumference of the toroid multiplied by number of turns per unit length. If I multiply these two, what I will get? I will get B is mu 0 Ni. What is B is mu 0 Ni? This is the magnetic field induction along the axis of the solenoid. Along the axis of the solenoid. That means the value of magnetic field inside the toroid along the axis of the toroid and value of magnetic field induction along the axis of the solenoid in the central part is exactly same. In the solenoid, since solenoid has two free ends, magnetic field here is very weak. So therefore magnetic field here in the central part of the solenoid and magnetic field along the axis of the toroid, they are exactly same. Here we find magnetic field in terms of number of turns per unit length. Here we find the magnetic field in terms of total number of turns of the toroid. So this is the difference between these two. Now we have to calculate magnetic field at the point P. So what I have to do? Again I have to use the Ampere circuital law. So what is B dot dl at the point P? B dot dl at the point P. Initially I assumed that at the point P there is a magnetic field, and this magnetic field is also in this direction, similar to the point S. I assume that at the point P there is a magnetic field which is similar to that at S. So therefore what is B dot dl at the point P? B dl cos 0 1. So B is constant at every point if it exists. So B integration of dl. What is integration of dl twice pi r? Okay? এইটো ৰেডিয়াছটো লৈ কনফিউজ নহবা, ৰেডিয়াছটো লৈ কনফিউজ নহবা কিয় আমি আগতে কৈছো নহয় our thickness of the toroid is very small. Our thickness of the toroid is very small. So under that situation, radius of this Amperian loop, radius of this Amperian loop and radius of this Amperian loop can be taken equal. So therefore, what is B dot dl? What is B dot dl at the point P? But what is B dot dl through the Amperian loop passing through the point P? So B into twice pi r. But this Amperian loop encloses no current. Inside this Amperian loop there is no current carrying wire. So therefore I 0. If I is 0, so if I is 0, what we get? B into twice pi r is equal to mu 0 into 0. So therefore B is 0. That means in the central part of the toroid there is no magnetic field. Now we have to find out what is magnetic field at the point Q. What is the point Q? It is outside the toroid. So what is B dot dl? Again B dl cos of 0. So closed integration of B dot dl around the Amperian loop passing through the point Q is equal to B into integration of dl. What is integration of dl? Again twice pi r. That means that if we calculate closed integration of B dot dl at the point S around this Amperian loop, or B dot dl, integration of B dot dl around this Amperian loop or around this Amperian loop, it is B into twice pi r. But now what is the current enclosed by this Amperian loop? Inside this Amperian loop there are two wires. One current enters the plane of paper and one current is out the plane of paper. This current entering inside the plane of paper and this current come out of the plane of paper. Okay? Equal number, this for every wires. So there is a wires here. That means if n number of wires are here, through these n wires current enters the plane of paper and through these n wires current is out of the plane of paper. So therefore what is total current inside the Amperian loop? It is Ni plus N minus I. Therefore total current inside the Amperian loop is 0. For the Amperian loop passing to the point Q, therefore P is 0 at the point Q. So this is the magnetic field induction. We've derived the magnetic field induction along the axis of the toroid, inside the toroid and outside the toroid. We have seen that magnetic field exists along the axis of the toroid, but magnetic field here and here is equal to 0. What is magnetic field along the axis of the toroid? It is B is equal to mu 0 Ni by twice pi r. What is N? N is the total number of turns of the toroid, and what is R? R is the radius of the toroid. Thank you.